We're going to be covering today, going a little bit deeper on algorithms, and very pleased to have Pantonium's CTO and co-founder Khun Yee Fung joining us. And it's going to be a nice opportunity for those that are joining to hear from essentially the creator of our macro transit on-demand platform about why the platform functions the way that it does, how it functions compared to other algorithms that are on the market today. And I want to encourage people to ask questions, right? Because these topics are not simple to understand. And so if there's any kind of clarifications, I'd like to keep this as a good open discussion, preferably in the Q&A window. I am going to be monitoring the chat. So fortunately, you don't have to hear me talk during this whole webinar. And without further ado, I just want to introduce Khun Yee and welcome him to the webinar series. And thanks, Khun Yee, for joining us today. Just to get a little introduction about yourself, just tell us a little bit about why optimization algorithms fascinate you, and a little bit about your background in working with these characters. So,
thanks, Jeremy. Well, the first time that I encountered this kind of algorithms, as every computer science student, sooner or later you encounter is usually in the theoretical computer science course in university. And it's always about the traveling salesman problem that they will talk about. Usually in the context of, that it is a very difficult problem to solve, and that it is a representation of a class of very difficult problem to solve, right? But as most other computer science students, I did not pay a lot of attention to it, right? Until about 15 years ago, when I joined the logistics company, when we actually had to deal with optimization, so route optimization. So that's basically routing, right? And it was a very fascinating time at that time, and it was a very interesting topic, right? Because at that time we finally had the hardware to be able to do routing well, and not really in real time, but at least to be able to do it in minutes or even hours rather than days before. So it was very interesting. So I started writing automation implementations, right? And that was the beginning of this whole thing. And then later on, when we founded Pantonium, right from the beginning, we realized that we would need optimization for routing as well. And then when a few years ago, when we had the chance to implement ODT, we finally basically had the opportunity to create a wonderful real-time optimization program that I always wanted to do, but never had the chance to do. So this is actually a wonderful opportunity. If you like algorithms, this is one of the most fascinating areas to think about, and it is extremely difficult, but it's fun. It's a lot of fun.
Well, it's definitely been fun over the last couple of years putting this theoretical into reality. And so why don't you get started with the presentation that we've got ready here, and let's take the folks on the phone through it. And
again,
let me
share the screen. And can you allow me to share the screen?
That would be So once again, folks on the phone, if you want to ask any questions during the presentation, please feel free to put it in the Q&A. And are you able to share your screen, Khun Yee, or is it?
No.
Or Jeff, can we give him permission?
Yeah.
Please?
Okay. Now I can. Okay. Let me do that. Okay, you can see my screen now.
See your backdrop. Yeah.
Yeah. Good.
Perfect.
Okay, now let me start. Okay, today we're going to talk about routing algorithms, and this is the component of the ODT system that determines how the system is going to run, right? And also how well it is going to run. Jeremy already introduced me. My name is Khun Yee Fung. I'm a co-founder and a CTO of Pantonium, and that's my email address, kyfung@pantonium.com. So if you have more questions or any, and just want to talk about routing algorithms or technology in general, okay, send me an email. So in the title, we have two terms, right? One term is on-demand transit. The second term is routing algorithms. So what are they? On-demand transit is basically, a system, a service that allows the riders to book a trip, right, or ride, however you want to call it, and they tell you when and where they want to be picked up and dropped off, right? But this is a very broad term, obviously, right? There are many ways that you can do it and still call it an on-demand transit, right? For example, is it going stop to stop, or is it going door to door, right? Stop to stop is more like the traditional transit, and it's a lot more efficient for the agency, right? But door to door is more convenient for the rider. But as usual, for a public transit, we have to, find a good balance between these two things, right? How efficient it is for the agency to provide the service, and how convenient it is for the rider to use the service, right? It's usually you cannot just consider, okay, make sure that the rider is the most convenient one. I mean, obviously, if you go to the extreme, right, the most convenient transport service for the rider is obviously something like a taxi ride, right? But then we are not talking about transit anymore, right? And also other things, right? What kind of cancellation policy you're going to have for your on-demand transit? And is it, has to be hours before, or you actually can handle it, so there is no cancellation policy? Although usually it's a good idea to have some kind of cancellation policy. And what kind of booking policy do you have, right? Can the rider book as soon as possible, right? So they have to book something, ahead of time, like 20 minutes from now, half an hour from now, right? And also whether the service, forces you to have transfers, right? So if you go from one part of the city to another part of the city, how many transfers do you need, right? None, 1, 2, 3. So, all these things, they seem to be, like features of a system, but they actually, all of them have something to do with the routing algorithm used in the system, okay? And, so because on-demand transit service is really managed by a on-demand transit software system, right? So the system obviously has a lot of components, right? We have to be able to configure it. We have to be able to manage it. You might allow the agency to do dispatching. You have to manage the users of the system. You have to be able to manage the riders and other things, right? And so the routing components is really one of the components that every on-demand transit, software system must have, right? But people don't tend to talk about it, right? So for whatever reason. But this is actually the routing. This is actually the component that determines how the service is going to operate and it will determine whether other features can be implemented at all, right? Or well, right? I mean, sometimes you can implement a feature, but it's not, it's not easy to do it well. Okay, so what are routing algorithms, right? A routing algorithm is basically can be defined as follows, right? Given a fleet of vehicles and a bunch of trips or rides, the routing algorithm assigns the rights to to the vehicles, right, in such a way that you want it to use the fewest of vehicles as possible. Even if you don't have to do that, you still want to know the demand, right? And then obviously you want the lowest mileage, right? No or fewest lateness for the rides, right? Shortest riding times for the riders, right? So all these things, if you look at them, it is basically an optimization problem, right? Obviously, you want the fewest, the best, and everything, right? So that you can run your service as efficient as possible, right? So this part, is, you can see it actually has something to do with the efficiency of the transit and also the convenience, for the riders, right? And the other thing that is a bit different from other optimization problems, especially for this kind of routing algorithms, right? In the old days, traditionally, routing algorithms are ahead of time kind of, thing to do, right? So you do it 1 day before, 2 days before, right? But for on-demand transit, it has to be done in real time, right? So, but what do you mean by real time, right? How real time is it? Is it a few seconds, a few minutes, and how much time do you have to come up with another plan, another solution, right? Is it in a minute? Is it good enough? Is it do you have to do it in a second, or even a fraction of a second, right? The reason why you want to do it in real time is because when you have cancellations, right? Then how do you handle that, right? How well can you handle that? And you also have certain changes, right? Or for example, if you want to allow the ad hoc boarding, you obviously need the system to be able to handle that in real time and very quickly, right? So those are the parameters you can see, right? For a routing algorithm, and also what it is trying to do. Okay. So, so the routing algorithm used, or the routing component used in the on-demand transit software system determines, how well the system, the service is going to operate, right? It actually determines the cancellation policy, and we'll see all these things. I'll explain why. The booking policy, whether there will be transfers, how many vehicles can be used, and even how to coordinate with other services, right? Because coordination with fixed routes, for us at Pantonium, we think that the coordination with fixed routes, so regional transits and rapid transits and other things, will be one of the most important aspects of ODT, on-demand transit, right? So what are the major properties of a routing algorithm? Well, the first thing is how many vehicles can it handle, right? Can it handle only one? Can it handle more than one? 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And how many rides can it handle at the same time, right? Is it 5, 4, 100, 200, 1,000? And how real time is it, right? So if an event or something happens right now, right? How long does it take for the system to handle it, right? So it's how real time it is. So when you look at a routing algorithm in the context of on-demand transit, these are the things that you think about, right? And let me move a little bit and talk about how a lot of people look at how to introduce on-demand transit, right? So these are very common steps in rolling out on-demand transit service, right? So people want to have something that's easier to control, right? So they choose a small area, they use one vehicle, right? And then they run it and see how well it performs, right? And see whether they can find problems with this situation, and maybe can fix problems, right? And then after that, right, once they know all these things, they say, okay, let's expand it to a bigger area, right, and more vehicles, right? And now that you have learned everything you need to know about ODT, but the thing is that routing algorithms are quite funny in this way, right? A lot of algorithms that can handle one vehicle cannot handle multiple vehicles, right? So whether you use one vehicle algorithm or an algorithm that can handle multiple vehicles, we actually change the characteristics of the service you're going to provide, right? So what is special, so special about routing algorithms then, right? Well, because routing well is difficult, right? In computer science talk, speak, routing is an NP-hard problem, right? So what it means is that it belongs to a class of algorithms that is considered almost the hardest, right, possible, right? So what it means is that, right, is that there is no fast algorithm to find the optimal solution. If you have a big enough, if you have a few vehicles, enough vehicles, right? If you have 5, 6, 7, 8 vehicles, and you have 200 stops, for example, right? How long does it take to find a solution, right? And in this case, if you want to find the optimal solution, then you actually have to look at every possible solution and find out which one is the optimal one. So it is what we call factorial kind of complexity. So if you have 20 stops and you can, you only have one vehicle, but you can try 1 billion solutions in 1 second, and it still take 77 years to do it, right? And then if you add one more stop, 21 stop, it will be like more than 100 years, right? So routing algorithms are like this kind of algorithms, right? So if you want to do it in real time, right, you cannot do it in the brute force way of actually checking every possible solution, right? So all good routing algorithms running in real time, in the real world, right, they try to find the best solution in a set amount of time, right? So for example, 2 seconds, 5 seconds, 10 seconds, a minute, right? We aim for milliseconds because, once you have enough riders and enough vehicles, right, you do get events that are coming in, under a second, right? So, whenever you get an event, you have to handle it. You have to come up with the next plan, the next solution, right? So the aim is always to get it in milliseconds. So what is a good routing algorithm? Well, it has to produce good routes in reasonable time continuously, because we are talking about on-demand transit, right? You cannot simply just do it once and then, follow it for the whole day. We cannot do that. And it has to be good enough because then you don't have to worry about, the second point, right? Provides, short waiting time for the riders, and you don't want riders to be on board for too long, right? And in our case, we always aim for, at most one transfer to go to rapid transit, to go to other services, right? If it is within the ODT service, right, it shouldn't have any transfer. And obviously, the last bit, you want to use a reasonable number of vehicles, right? You might not be able to find out what the minimum number of vehicles you can use for a certain day, but at least it is reasonable, right? Not one vehicle per ride, right? So that would become a taxi service. So what happens if you don't have a good routing algorithm, right? So what do you do, right? So usually, as a very important technique is to do divide and conquer, right? So if you have a big service area, then you can handle it with one vehicle. You chop it in multiple zones, right? So each with one vehicle, then you can have a less optimal, I guess, a less good algorithm to handle the small zones, right? Because the problem becomes smaller, right? Or you don't handle real-time events as well, right? So you take a bit more time to do it, so that you have more time for the system, for the algorithm to process the events, right? But although divide and conquer is a good technique in general, right? It's just not a good idea. I don't think it's just a good idea for ODT, right? Because if you want to use ODT to ODT service to replace a particular fixed route, it's not a good idea, because a fixed route usually can handle a lot of a big area, right? If you look at the typical fixed route, the catchment area is actually quite big, right? And the productivity, if you use ODT to replace one single fixed route, right, the productivity is going to be the same, right? I mean, you still have the same riders, right? Same number of riders, so you're not going to change very much. And a lot of fixed routes have very productive segments, right, and non-productive segments. And for the most productive segment, it might be too productive for something like the on-demand system to handle, or at least you don't want to use that to handle that kind of segments. And it's just not flexible at all, right? It's difficult to adjust, right? If you have multiple zones, how do you adjust to find out which vehicle should go where and how many vehicles should be here in this zone and this, and also if the demand fluctuates, in a day, how do you separate, how do you divide the area into zones, right? And if you have rush hours for certain zones in the morning, and how do you do that, right? And if you have a zone that becomes very busy, how do you add another vehicle to it, right? If the zone requires 3 vehicles, then you still have a problem, right? I mean, if you cannot handle 3 vehicles for your routing algorithm, now you still have that problem. It's not going to change anything. And for a lot of zones, if they are not very productive, what do you do, right? If the demand is really low, right? You cannot reduce the number to 0. Well, I guess you can reduce it to 0 if you outsource it to taxis or other things to handle the rides, right? And then in a lot of situations, if the zones are quite big in low on-demand areas, then you have to make them overlapping each other, because otherwise you're going to have a lot of transfers, right? And other things, right? And for the riders, it's actually not very convenient, because you almost have to guarantee in a more urban area that you need 2 transfers, right? Unless you're going downtown or somewhere that is very popular. Otherwise, you probably need 2 transfers, right? From a zone to a fixed route, and then take the fixed route, and then you have to transfer again to get to another vehicle on the on-demand service, right? And if you have to do a transfer from a fixed route to another fixed route, now we are talking about 3 transfers for a ride. There's a little bit not ideal, right? And you might have long wait time for transfers as well, right? So these are all the problems with zoning. If and if you don't have a very good algorithm that actually can handle a lot of vehicles in a large area. So types of routing algorithms. Let's talk about the one vehicle algorithms that these are the 4 classes of one vehicle algorithms that I can think of, right? Over the years, over the last 15, 16 years, right? I actually have implemented all of them in one form or another, right? Sometimes because I needed a quick and dirty kind of solution, right? Sometimes it's because I don't need a sophisticated algorithm to handle a very trivial case. Like, for example, 1 vehicle and I only have 3 rides, right? If you have 1 vehicle and 3 rides, use the brute force method, right? I mean, it's going to take you how many? 6, 7 solutions, right? To find the optimal solution. There is no need to do anything more sophisticated than that, right? But obviously, when you start having a bigger problem, then it is difficult to simply just use brute force, right? Best position is another algorithm that's quite useful if the route is quite static, right? So basically, what you do, you just check, you just try different positions for the pickup and the drop-off stops, right? And then you find the best, position for them, and then you just insert it that way, right? So that's what I call a best position algorithm. The greedy algorithm is the most intuitive one that most human dispatchers use, right? Basically, you choose the closest stop to the current stop and treat it and use it as the next stop, right? So that's the greedy algorithm. Don't know why they call it greedy, but I guess I would call it expedience, right? So it's probably a better name for it. And then obviously, if you start having a big, a long route and you have a lot of rides, right? Then you use a TSP solver, the traveling salesman problem solver. So if you have never heard of TSP, the traveling salesman problem is basically, given that, say suppose you're a salesperson, and you have 10 cities that you have to visit one by one, right? So, find the most optimal way of visiting all of them, right? And that's called I mean, in terms of something, right? In terms of a distance, right? Or in terms of the plane ticket, cost that you have to pay, or whatever, right? So the whatever that you define as important for you as the cost, right? So you're trying to find the optimal way of doing it. So that's called a traveling salesman problem, right? So a TSP solver is basically a program that can get you the optimal solution, or in real-time situation, a good enough solution. Okay, so let's look at all these algorithms a little bit more. So the first one, I call them random first come first serve brute force, right? Basically you just do whatever you want to do, right? First come first serve. You just insert the first write into your system, and then when you get the second one, you insert it to your system, to the root, right? I mean, because you only have one root, if you do it that way, basically, it looks like a taxi service, right? That's basically it. So how many writes can you do if you have a first come first serve service? I mean, algorithm is probably about 4 or 5, and I assume that you do it door to door, right? Or random, you just assigned it, see how it goes. I actually implemented something that looks like this for the first step of the algorithm, right? So you actually want to randomize it so that you have a solution, but it's not a good solution, right? And then you start from there and see whether you can get a better solution. And obviously, the initial solution is horrendous, right? And it's not going to be good, right? And it's always bad. Basically, the root quality is going to be very bad. When I mentioned the phrase root quality, I mean, how many writes can you do in an hour, right? And how long do the writers have to wait, and how long do they have to stay on board, right? So all these things together, right, define what the quality of the root is, right? For the agency, obviously, you want to be able to handle as many writes as possible in an hour. But for the writers, obviously, they want to be able to wait at least the shortest time, and they don't want to stay on board for too long. So those are the 3 major things that you look at to see how good the root is, right? Or the third thing that that you can do, right? This one is not really an algorithm, right? You just get a human to dispatch it. So you just get a person to add the trips into the root, right? I mean, is anybody doing that behind the scene? I don't know, but it is possible. You need a very experienced dispatcher. Otherwise, they'll probably just use the greedy algorithm, right? Just find the closest closest stop as the next stop, right? And then you'll be doing it manually rather than automatically. For brute force method, it's not advisable if you have, more than, I would say, about 12 or 13. If you have an incredibly fast computer, right? I would say the limit is about 20 stops. But we are talking about almost a minute to find the optimal solution. And, because things change so fast in the real world anyway, finding the optimal solution is really not the goal, right? A good enough solution in reasonable time is, right? So brute force can still be useful, like as I mentioned, because if you have only a few writes, right? Brute force is actually not a bad thing to do. But once you have more than 10 or 11 stops, it's basically not a good idea. And I already talked a little bit about best position, right? So what you do is you just try, first you look at the pickup stop, you try it and insert it in every position possible in the root, right? And then you insert the drop-off point as well. So you try every position, right? And see what is the best combination, right? For the positions for the pickup and position for the drop off, that gives you the best route, right? In terms of the route quality, right? The thing is, right, the order that you insert the writes determines how good the route is, right? Which is not a very good property at all, right? So you can have the same 3 trips, but if you don't insert them in the same order, they might give you 3 or actually more than 3 possible, so-called good routes, right? I mean, or possible routes, and but the thing is, we cannot determine how the rights are entered by the writers. Cancellations for sure will make it worse because if you cancel a write, right, suddenly a good A, B, C kind of order becomes bad, right? Because if you miss B, you go to A, C, and if the next one is D, you probably want to go A, D, C probably, but you don't know, right? But for best position, you cannot do that because the right will basically stay in the same position. If you have a very short service, like 1 or 2 hours, right, or even less than that, and very few writes anyway, right, 2, 3 writes an hour, right, best position can be used, right? But there is another nasty property of best position is that it doesn't handle request time very well, right? But at least it can handle it, which is not true for some other algorithms. For example, greedy algorithm, right? Greedy algorithm is basically, choose the closest stop as the next stop. Right? Number one, is the closest stop is not always the wise stop to choose, right? It's not always the good one, although it's just the closest one. Because if you think about it, right? If closest, it is possible to move the vehicle to one area of the service area quite easily, right? If they are all stringed together, on one side of the service area, and then you might, it'll be very difficult for you then go back to the other side of the service area. Okay, and it is very bad for request time because you have 2 things now, right? So you have the closest distance, and you have the closest, right, you have to handle, right? How do you find out, what the closest stop is, right? So a lot of ODP systems, right, if they use a greedy algorithm, they basically don't allow you to have a request time. So you cannot say, you cannot book a trip 2 hours from now, or you cannot book a trip and say, I want to be dropped off at 5 p.m. Right, so they only allow you to be as soon as possible, right? So, and even then, they still basically, will give you, say, a 20 minutes lead time, right? It's simply not easy to handle these 2 parameters at the same time, right? And obviously, you can do, you can modify it a little bit and don't just look at one stop. You can look at 2 or 3 stops at the same time, right? And try to find where, how to order them. Right, and the other thing is that in theory, right, you can handle ad hoc loading, but in practice, it's probably not a good idea because the route quality is not good in the first place, right? And you really don't want to make it actually more difficult to do. So the actual solution for one vehicle problem is really, a TSP solver. I already talked about it, and but it needs to be a real-time TSP solver. A lot of TSP solving, methods, right? They do need a bit of time to get you a reasonably good solution, right? So that is a problem because if you have to do it in real time, how do you make sure that you can find a good enough solution quickly, right? It is actually not an easy thing to do. But at least once you have that, the route quality is going to be as good as possible all the time, right? Because you will always find the least bad solution for you, right? Even if you have cancellations, right? If you have cancellations or even no shows, right? It will be able to, to come up with something to compensate for that, right? Which is not true for greedy algorithm, for example. It is definitely not true for best position, and for the random, all these other things. Well, they are not giving you very good solutions in the first place. Right? So there are there are two classes, I guess. There might be, you know, there might be others, right? But these two seems to be the you know the more popular ways of handling multiple vehicles, right? One way is to do what I call insert to best vehicle. So it's basically a scaled up version of best position, right? So instead of just looking at one route, you look at every routes, right? And when you have a right to insert into your system, what you do is you try to insert it to every route, right? And see which one, I mean, using the best position algorithm, right? And then you see which overall solution is the best, right? So, and then in that way, you choose the route to insert, right? That particular right. But that algorithm, right, has the same nasty properties as best positions, right? Is that the route quality gets bad very quickly, right? And it gets bad no matter what along the way. And the order of writes, you know, inserted or, you know, booked by the writers actually means something, which is not a good property to have. And you know, again, you know, there is a solution to it. The solution really is to get the real-time global optimizing routing algorithm, right? So you continuously optimize the whole fleet and all the trips, right? So let's look at these two algorithms a little bit more. So like I say, it's basically to scale up the best position algorithm from one vehicle to multiple vehicles, right? Or one route to multiple routes. That's basically it, right? And you know, one of the things that drives you know, the optimization for a multiple vehicle, multiple, you know, routes kind of scenario is to allow rights to go from a route to another route, right? So the reason is that that's how you can balance, you know, the different vehicles, different routes, right, in real time, right? Because you know, because a certain area of a service area might get too busy, so you want to move vehicles along to there. But the thing is, you might want to basically assign the trips that were actually on the route to some other routes that are in the area. So you have to be able to do that, because if you cannot do that, right, you know, you won't be able to balance the demand quickly and in real time, right? So imagine a scenario where you have 5 vehicles in the beginning of the day, right? The demand is spread out very nicely, you know, in the service area. So the vehicles are spread out widely in the service area, right? And then suddenly one corner of the service area gets a lot of, you know, rights. What do, right? So now you have a situation where, you know, the vehicles that are actually near the area will get a lot of rights, but the other rights will still be too far away, right? So you can actually consolidate the rights. For example, if you have 3 vehicles in you know, on the east side, right? You cannot then say, okay, let me move all the rights on all these vehicles to 1 vehicles and move everything else. So 3 vehicles, 1 stay, 2 go to the higher demand area. You cannot do that, right? Because it doesn't move. You know, once the trips are in the routes, they stay, right? I mean, you know, you can call it a virtue if you want, right? Because once a trip is assigned to a route, it doesn't go away. It stays on that vehicle. So that's the only thing that I can think of that is actually good, you know, if you use this kind of algorithm. Again, you know, there's a right way to do it. The right way is really a real-time global routing optimizing algorithm, right? So, you know, this kind of algorithms will handle a large area with all the trips that you have and all the vehicles that you have. It shouldn't need any transfers at all, right? If it's a good algorithm, it shouldn't need any transfer within the area. And cancellations wouldn't be a problem because you can move trips around, so you can balance the demand at the you know, how many rides on each route very quickly, right? Even no shows, right? You know, if you have a no show, the vehicle arrives at the pickup stop, right? And then you have nobody boarding there. A real-time global routing algorithm will basically just get rid of the drop-off stop, right? And then it will try to optimize and see what is the solution again, right? So you lose one stop basically, right? And cancellations is not a problem at all, right? Because if you're not on your way to the pickup stop, right? The algorithm should be able to just get rid of the trip very quickly and easily, right? And this kind of algorithm will also tell you, how many vehicles you need to handle that kind of a particular kind of service, right? So even though you might say, oh, I have 10 vehicles, I want to use all 10 of them, right? Yeah, sure, it's not a bad idea, right? If the algorithm then uses only 9 of them, you have one idle vehicle, and if something changes, right, you have one idle vehicle that you can use for that purpose, right? So it gives you more flexibility no matter what, right? And if your aim is to find out the minimum number of vehicles you need, then this algorithm will tell you, right? I mean, if you need only 9 vehicles rather than 10, it will tell you only need 9. So you can actually take away the one vehicle. Because it is a real-time system, right? You can just take away the idle vehicle without any problem, right? Because it will be able to just adjust itself and handle only 9 vehicles, right? And definitely can handle ad hoc boarding. So basically, when a rider just boards the vehicle and say, oh, I would like to go there or to go to a particular place to be dropped off. Yeah, it has no problem, right? Because it can add in the drop-off point, easily, and in this case, it has to be the same vehicle, right? So what it means is that it can take away rides that are on that vehicle that meant to be for that vehicle, but that have not been picked up yet to other vehicles if necessary, right? So it allows the balancing of the vehicles in real time. And you can also book drop-off time now rather than just pickup time, right? And because it is real time, right? So you can also coordinate with fixed routes much easier and rapid transits, right? And because it's multiple vehicles, you don't have to designate one vehicles to do that or the other one. It makes it a lot more flexible. So for example, you can set a time that rapid transit, say regional transit or commuter transit, something, right? At 10 o'clock, it arrives at a certain place. Right. So what you do is just basically say, okay, when the time comes, so I'll make sure that we have one vehicle waiting there at 10 o'clock, right? For that particular transit to pick up the people. And because you can allow ad hoc boardings, right? They don't even have to book the trips, right? They can just board the vehicle and tell the driver or set up where they want to be dropped off, right? So it can be very flexible that way. Right, and you'll be able to handle very long trips well because you have if you have multiple vehicles that you can use to balance each other out, right? Long trips can be handled well that way, and also there are other possibilities that you can actually do it to make it even better, right? I mean, we have, for example, at Pantonium, we actually have a method to handle really long regional trips, right, and not be impacted by it too much if there is a cancellation or there's a no-show, right? And the last one, allowing driver to detour. This is actually something very interesting, right? Is that because it's real time and it optimizes everything at the same time, right? In some situation, if the driver actually knows that somebody is actually waiting, say, not too far away from the current stop, right? The driver can basically just say, okay, I'm going there. And as long as the driver informs the system that, they are going to that stop, right? They can do that because the system will be able to just adjust again, right? Everything, and then allow that vehicle to go to something that's actually not scheduled by the system. Okay, and allowing rides to move from route to route is really the way to maintain and improve route quality, and that is really the key thing that differentiates multiple vehicle kind of algorithm versus a one vehicle algorithm in many zones, right? Because it allows you, the flexibility of adjusting to the demand. So, say suppose you have an on-demand transit system, right? You want to find out which kind of algorithm is used in that system. This is a table. These are general characteristics, right? I mean, but these are more or less how you can find out, right? So first thing is how many writes can we handle per hour, right? That more or less tells you how efficient the routing algorithm is, right? It depends on your service area too, right? Obviously, right? But in general, this is how you look at it, right? I mean, real-time global optimization algorithm can handle many, right? We have seen over 20 in our experience, right? 20 writes per. When I say a ride, right, I'm talking about how many passengers, how many riders, right? Is how many rides. So if one ride, somebody books a ride with 5 people, is considered one ride for us, right? Because for routing, it doesn't matter, right? It's not how many people you can carry, it's how many rides you can carry. So you have seen over 20, right? Greedy algorithm, I'll say about 5, because the routes will get imbalanced very quickly. So, best position and insertion, the insert to the best route algorithm. This too is tough to tell because the route qualities are so bad. I'm not sure, if you can handle certain number, what does it mean, right? If every one of them is so late that I'm not sure, do you count that, right? I guess you can count that, but so for real-time TSP, same thing, right? You can handle a lot of right. So I would say about 10, right? Because TSP solvers has one. They have one characteristics that's different from real-time global optimization algorithm is that, like I said before, right? It takes a little bit of time to start up, right? To start giving you good solutions, right? So the aim is to get to a good enough solution. So TSP solvers need a little bit of time to get you the first good solution in general, right? And if you don't use algorithm or brute force, it's about 5. And obviously the number of vehicles and zones, right? I mean, this is the big one, right? Is, if you look at it, it's only 2 algorithms that can, that actually gives you that one zone with, all the vehicles and all the rights. And for greedy algorithm, these are the one vehicle algorithms that we talk about, right? Obviously, they are for one, and then if you don't use any algorithm, I don't know, right? I mean, it depends on that particular method that you're using. Cancellation policy, right?
I don't mean to interrupt, but we're getting close on time, and we do have some questions that folks want to answer, and I think that if folks want to look at this table, the recording will be available for them to go back and use it as a resource, because I think this is a very powerful tool that folks can use to assess the capabilities, right? And definitely think it's a great way to reference it. But with only 10 minutes left, I think it might be good if we could advance and maybe get to some
you can
questions.
move on. Yes. Actually, I'm almost done anyway. So so the reason why not everybody is using a global routing or optimizing algorithms, because it is actually very difficult to create and implement, right? So that's really the reason. And to be real time, it is extremely difficult, right? And but at Pantonium, we actually created and implemented a real time global routing optimization algorithm. So it is global, it's real time, and it's flexible, right? Because if it is global and real time, it will be flexible. Our goal is to provide the effective on-demand transit service, right? So it is convenient for the riders and efficient for the agency, right? So it's not just one or the other. And one of our deployments run 9 concurrent vehicles in one zone, comprising the whole city. So that's there's the city and there's all the stops, right? So basically we have 9 vehicles running around in one zone, okay? And we also have a real-time TSP solver. And so does it mean that all we need is the right routing algorithm? No, but it is necessary, right? So it's what we usually say. Is it necessary? Is it sufficient? It is necessary. You must have a good routing algorithm, or you're not going to have a very good OTT service, right? So because the routing algorithm determines how well it's going to run. Is it sufficient? Obviously, it's not sufficient. You need other things as well, right? Other things to make sure that the routing algorithm will run well. Okay, so that's my presentation.
There's definitely a lot of material, especially for folks who are not, doing routing algorithm design day to day. And I think there's gonna be a lot of opportunity to go back and take a look at it. I think it's a great summary, and more resources will come along. And also folks that are interested in kind of the comparison. The whole point of running through these types of algorithms is for you to assess, the type of service that you're looking to deploy, and be aware of the pitfalls of certain characteristics. So by looking at deployment characteristics, there's another webinar that's recorded about what is macro transit, which is the terminology we're using for our global optimization algorithm platform, is to look at the characteristics that you want to achieve and compare that with what's available on the market. And so we're trying to be very open and honest about what we can do with our platform. And I think that's very important. Now, to get a couple of questions, someone asked Khun Yee, you've put all the work into to write all this algorithm. It's something that we've spent a lot of time and energy on. How do you protect it? How do you stop it from being borrowed or quote stolen?
Well, ultimately, there's no way, right? I mean, just there's no way. And but the thing is, for example, when I talk about the real-time global optimizing algorithm, right? There are lots of ways to do that, right? Obviously, I don't think the way that we do it is the unique one, right? But as if you know algorithm design, right? Getting the algorithm is the first step. Okay, you must have a very good algorithm to start with, but to actually implement it right efficiently and in the right way for your context, right? That is also very important as well, right? For example, just give you one simple example, right? Almost everybody knows how Google is doing search, right? I mean, the algorithm is well known, right? But their particular implementation, their particular way of doing ranking, right, is trade secret for them, right? So knowing the algorithm is one thing, right? Obviously, you need one, right? I mean, you need an algorithm that can handle billions and trillions of web pages, right? But how you implement it is also important, right? So in our case, that's why I said we created one. We created a good algorithm, I believe. And we also implemented it so that it is extremely efficient. So we are talking about sub-millisecond kind of running time for us, right? If you just implement it, the algorithm in the naive way, right? We'll be talking about seconds or if not minutes.
We have another question about coordination with other transits, so like fixed route schedules. How does the algorithm work with a fixed route schedule to do that coordination?
Yeah, say suppose you have real-time GTFS, right? That you publish, right? Or a transit publishes, and you want to coordinate with that, right? And the time, the pickup time or the drop-off time changes all the time, right? So each time that it changes, right, it is an event to the system, right? The system will then just take it and changes the time for the connecting right, and re-optimize it, reroute the whole thing, and come up with the best solution for that particular change. So that's why it has to be real time because of that reason. And the reason why a global algorithm is good is that you might actually decide to use a different vehicle, right? If the connecting stop is going to be 10 minutes late, right? A different vehicle might be a better choice. Right? So that's how you can coordinate with with real-time changes in other services.
And in terms of the rider experience, the time period to get them to that transfer point or that transfer situation, the lateness is actually kind of a negative. It's a harder criteria, right? That you want to make sure they get there on time.
It's actually not always a bad thing, right? For example, say you're taking ODT right now, right? You expect to be dropped off in 15 minutes for a connecting ride, right? For a transfer to a rapid transit, for example. But the rapid transit is 10 minutes late, right? And it's 10 o'clock p.m. right now. Do you want to wait there for 10 minutes or you rather be on the bus for that extra 10 minutes? As long as you know that's what is happening, right? That the connecting stop is actually going, the connecting ride is going to be 10 minutes late. And you rather be on the bus, right? I mean, especially in the winter, right? So at least you have the flexibility to allow that to happen, right? Obviously.
A couple more things about topography. Do we look at any sort of geographical impediments, like particularly hilly terrain or choke points, to try and avoid, those scenarios, to try and route through that, which could increase fuel cost or other things like that?
Yeah, so it's basically what we, when we decide what's the best way, what's the best next stop, basically, right? You look at what we call the cost, right? And how you determine the cost depends on different things, right? It doesn't have to be the distance only. And distance, what kind of distance, right? Is it the straight line distance or actually the road distance, right? The traveling distance. And is it the time, right? How long does it take from this point to the next point, right? And, usually what you do is you actually use the traveling time because that will take care of all the topography, between the two stops, right? So if it's a hilly one and it is slower and the time to travel obviously is longer, right? And if you, for example, if you want to avoid all the, the freeways, right? And that you can take into consideration and basically just do not use freeways, right? To calculate the cost. So that's how you do that. And then you basically put in all these different parameters to find out, for example, a lot of traffic stops, or it is a downtown area is 30 or even 20 miles an hour kind of places. Well, because the travel time will tell you how long it takes, right? And with the travel time, you can also do other things as well, like it's a rush hour, so you add a 10% discount to it or 20% discount to it. So that's how you can handle all kinds of different parameters, including topography.
Talk about like a large metro area like Los Angeles, where there's 15 different agencies that don't necessarily work together.
Right.
How could ODT help people navigate in that type of an environment?
Yeah. So in, say, if it's just Los Angeles, right? I assume that you have some kind of commuter service, rapid transit, and all these other things, right? So what you do is you try to coordinate between, say, suppose you are just a small jurisdiction in that area, right? You really cannot force other jurisdictions to do what you want to do. Well, what you do is you try to make it as convenient as possible for your jurisdiction to connect to the other services. If you have, nothing that you can do about the coordination with something that's actually far away from you, right? So all these, practical things, right? I mean, they are not just, they don't depend just on algorithms, obviously, right? It depends on how cooperative the adjacent municipalities are. And, but ODT will still help, if you are a bedroom community, right? It will help you to handle the fluctuations in demands and different, demand patterns in your different areas, right? Because fixed routes tend not to do very well if the demand is low, right? You tend to have very long routes with very low demand. and OTT will cover that easily for you, right? And if you are in downtown Los Angeles, for example, and you are actually operating the transit service there, if even in that situation, OTT will still be very useful, because in most big metropolitan kind of areas, right, the fixed routes are designed to get to rapid transits, right? I mean, or to get to certain hubs, right? It's actually difficult for people to move around in certain community areas, right? It's not exactly local, but you know, so you tend to have situation where if you have to cross against the routes of the fixed routes, right? It's actually difficult. You have to transfer once, twice, or worse, right? OTT will still help in that kind of situation, right? And if you have to do coordination, you still can do that with if you have the GTFS, real-time GTFS. That's what you do.
There's an actually interesting question about for real-time global optimization TSP. How do you? I guess this isn't going to be an easy answer, but what kind of guidance would you give on how many vehicles to deploy? Is the only requirement more than one, or like, I know you have to go through and analyze this, but kind of give some tips on how to figure out the right number of vehicles to deploy for real-time global and TSP. So.
Well, for TSP, it's one vehicle, right? So
TSP is only one. That's right.
Yeah. So it's not much you can do about it, right?
But what about real-time TSP?
Real-time TSP is the same thing. It's still one
same
vehicle.
Thing. Okay. One
yeah,
vehicle.
But if you're talking about global optimizing, right, algorithms, right, you can do simulation, right, if you want to, and and then you can find out. And in general, it's very quick. Once you deploy it, it's very quick that you can find out how many vehicles you need, right? And this, so if you cannot do simulation, that's what you do. And then if you want to do it in phases, what you do is you enlarge the service area step by step, which we actually encountered in some of our customers, right? So you start with a smaller area, but still multiple vehicles, and then you just make it bigger and bigger and bigger, and you see what happens. So you add more stops to it, right? And add a transit desert to it, right? At the low demand place that you cannot handle very well right now with fixed routes to it, and see what happens, right? And very quickly it will tell you, because the algorithm gives you the minimum number of vehicles you need.
We are a little bit over time, but there's still a couple more questions. So I am going to continue on. Folks can stick around and be part of the conversation. I understood if you have to jump off, the recording will still be available. So talk about how regional transit could, like regional coordination. So numerous small transits want to coordinate travel between themselves.
Right.
Is it better for each of them to have their own system, or should they maybe think about banding together and using a common platform? So,
well, it depends, right? It depends how cooperative the jurisdictions are. Is always that, right? Say suppose because there are two models to look at, right? One model is actually everybody tries to cooperate. They still have their own transit agency to run, right? So this is something that I call, for example, if you're thinking about commuting, right? So so you have the origin, right? The first transit that you have to deal with, that's your own hometown or region, and then you want to transfer to a rapid transit, right? Because we are talking about a regional situation. It might not be a rapid transit, but it's just a regional transit, right? So you get there, and then when you're dropped off, you might have to take another transit to get to your final destination, right? So one way is to coordinate the first leg of it and the last leg of it, right? So that everything is handled properly, right? So they all cooperate, they use one platform to do that, but you don't have to do that. That's one way. Another way is basically if you use something like the Pantonium platform, right? But you're not actually using the one system, you have two instances of a Pantonium system, because you have two jurisdictions, right? So what you still can do is to make sure that you know, the pickup area, right, that coordinates with the regional transit or rapid transit well, right, and then the you know, the final destination that ODT also coordinates with the regional transit or rapid transit. In that way, even though there are 3 different jurisdictions, you have the originating jurisdiction, you have the rapid transit, and you have the, you know, you have the final destination transit, right? I mean, you know, with the coordination, if you have real-time GTFS for the rapid transit or the regional transit, right, you can actually coordinate that without really, you know, using the one instance of the platform, right? But the 2 platforms that you use on the originating and the final, you know, area, right? They have to be able to coordinate with the rapid transit or the regional transit well, right? Otherwise, you have a problem, right?
Right. What are your thoughts on the implementation of ride sharing or like Uber, Lyft platforms? Would you call those optimization, or are those just matching? So.
Well, I wouldn't call them well, they are optimization in a sense, right? It depends how you define the word optimization, right? If the optimizing criterion is to make as much money as possible, right, then obviously it is an optimization problem, right? But Uber or Lyft, they are not transit systems, right? So what it means is that they have no obligation to provide a public good, right, which a transit system must have. So the question of equity or fairness, right, doesn't even come into the equation for Uber or Lyft, right? For a transit system, on the other hand, the reason why we talk about all this optimization to, you know, short wait time and short, you know, ride time and all these things, and, you know, and buses and vehicles that belong to agencies is because they're, you know, public transit is providing a public good, so it has to have that equity component to it, right? Which Uber and Lyft don't have to, and the algorithm they use is whatever that they make the most money out of, right? So they can have, you know, all kind of different pricing schemes, you know, and then they can have a matching kind of algorithm, right, to maximize certain thing that they desire, right? And that certain thing doesn't have to be anything close to about public good or equity or fairness at all.
I think it's important because people need to remember that Uber started off as a direct competitor to public transit, and in recent years they've been cozying up quite closely with public transit as their model has kind of either hit a limit or kind of been encumbered with you know, some municipal legislations and things like that. So when they were breaking the rules, everybody was cheering them on, and then when things kind of started, you know, revealing themselves what their purpose was, it started to kind of, you know, shine a different type of light on that platform. But now they want to partner with public transit to try and enable first mile, last mile, you know, transportation. So, you know, do you think there is a fit for them in this space? So,
you know, anytime that you put equity into the equation, right, then Uber and Lyft just doesn't do it well, right? I mean, just the way it is because of the model, right? Even if they do carpooling, for example, right, it still have that same problem, right? And also, you know, I think it's sort of like a interesting way to just look at first mile, last mile as inside isolation, right? If you have a community that requires that kind of service, right, to a rapid transit for rush hours, for example, right, you don't just look at that in isolation. Actually, a lot of them do, but I don't think that is actually the best solution to it. The best solution is actually to combine first mile, last mile, and also community transit, you know, as one service, right? So that you know, you fulfill the first mile, last mile kind of service that you should provide, and at the same time, right, you are not forfeiting all this community kind of transport, going to the library, going to the community center, not just to the rapid transit or the regional transit. So looking at it as in isolation, first mile, last mile, I think is not the best way to go, but rather look at the whole community, what kind of service they need for, from transit. I think that's the best way to go forward.
We have one more question, and it kind of feeds into some other conversations that you and I have had in the past about other types of layers of information that you could use in the planning process, like real-time traffic information, or doing some machine learning on trying to best position of a vehicle while it's waiting for a trip. These things always kind of come up in the discussion because people want to know, are we doing these types of things? And I think that your answer is very interesting. So I'd like to just dig into that a little bit. So
yeah, if you have a global optimization algorithm, right? What you deal with is certainty, right? So you have these vehicles, you have these routes, right? You have these rights that you have to service. It's certain, it's 100%. You actually have to do it, right? In the artificial intelligence or machine learning or all these other things, they tend to talk about predictive, right? So you want to predict what the next stop might be, right? So it is a big difference, right? Obviously, because if you have certainty and you can do it well, right? Why not, right? If you know what the next stop should be, why do you care about the prediction of what the next stop should be? You already know what it is going to be, right? So that's the number one thing that you always think about, right? Global, optimization algorithms deal with certainty right now, right? If it's just real time, it deals with certainty right now. You actually have the whole, the whole thing in front of you. So how do you come up with the best solution right now, right? And then 1 second later, yes, you have a new reality, and then you deal with that reality right now, right? For example, we actually had a study, right, that they did for one of our customers using machine learning and AI. They actually came up with a model that they could predict 30% of what the stops would be, right? But it's 30%, it's not 100%, right? But in global optimization algorithms, we're talking about 100%, right? So we will find what the best stop for the next stop is, right? Rather than try to find out 30% of the time that it should be that, right? So that is the major thing, difference between, global optimization kind of algorithm versus predictive model. And yeah, so yeah, some other thought came into my mind. It was just promptly forgot. Sorry.
No, that's fine. It's also, you've been talking a lot, and we definitely appreciate you taking time. We're 15 minutes over time, but I think a lot of good detail. And again, I'm happy that you could take some time to join this webinar series and talk to folks about the complexity of these algorithms and how it's being deployed to help the technology transformation for public transit. For folks on the call, we do have another webinar coming up at the end of the month with our first implementations transit manager, Paul Buck from Belleville, talk about kind of the full circle of what they've achieved from going to on-demand and coming back towards a hybrid system of fixed routes and on-demand services working together. So Khun Yee, thank you for taking time. Thank you for all the hard work in putting this platform into make it come to fruition. And we definitely look forward to what's achieved here in 2021. So thanks, everybody, and we'll see you next time.